Welcome back. My name is Dan Maloney. I'm a staff writer here at Hackaday, and I'm here to take you through the last of today's talks. We're going to get started right now with our next speaker, who has nearly a half century of hardware design experience under his belt, has been around long enough to actually see something that he's designed be enshrined in the Computer History Museum, which is a big accomplishment. He comes to us today to condense down his life's work and tell us how to become a hardware expert in only 40 minutes. Please welcome Voja Antonic.
Hey, I'm Voja Antonic, and we will use these 40 minutes to understand the basic of microprocessor architecture. I have to speak fast because I want to make some time to show you something. But we will start from very basic logic circuits and build the hypothetical microprocessor part by part. And that will not be actually the fully functional microprocessor because it's a little bit simplified. I'm not sure that it would work, but it will be good enough to just to show the basic principles of microprocessor architecture. But before we start, it's important for you to know that you don't have to understand all schematic diagrams in detail. Don't try to follow every single logic level. It's enough for you just to understand the purpose of logic circuits and their input-output dependencies. There are also several points where you must learn about certain circuits. So you must pay the special attention, and those slides will be notified by the blue background. Just let me see how to share the screen like this. I hope that now you see the shared screen. I guess so. Just a moment.
Yep,
yeah,
looks good from here.
Yeah, good. So this is the normal slide, and this is the blue slide, which should just notify that something important happens and that you have to pay special attention. And there is something, if there is something extremely important, the screen will be red, like this. Actually, there is only one completely red screen, and we will the only one, but you will be surprised to see that it's also this is the simplest slide in the presentation. So it may be the simplest possible circuit that can be built. It will be the most important circuit. So let's talk about why digital electronics are so superior against the analog ones. Just a moment. I'm confused about this Zoom interface because I didn't use it too much. I have to do you see signal from camera now? I hope so.
Not yet, Voja. I don't see the other camera.
Just a moment, please. I'm sorry. Now you see it. Good. I prepared some short demo just to let me compare digital and analog electronics. This is the one of these screens, the left instrument that you see represent the analog signal. When I turn this button, then you can see that this instrument voltage rises or drops, and you see the LED above the instrument, which also follows that signal. The right one is digital signal. It can be only on and off. And why is it so important now? And why did we? What's the actual? Why is it why do we use digital electronics instead of analog ones? What's so good about digital electronics? look at this diagram. The price performance ratio for analog electronics is not so good for us. The price, when you increase the accuracy of analog signal, then you see that cost for analog circuit rises exponentially with raising the accuracy of the signal. And when you use the digital the circuit, then with every single bit that you add to the circuit, you raise the price linearly or approximately linearly, but the performance and accuracy doubles with every single bit added. That's what makes digital circuits so familiar to us, because we can achieve any accuracy that we want, and that's without rising the cost significantly, and that's the catch. But we are talking here about hardware, so we will switch back to the hardware circuits. We will use this the similar screen in many examples here. In order to build a circuit, we must have a current supply first. The 3-volt battery will be good enough for that, because most of digital circuits works well at 3 volts voltage. Minus pole is usually considered as the common ground, and it's used as a reference point for all voltage measurements. Here it is marked as blue. You see it here. And the red color represents the full voltage, 3 voltage, or its logical signal 1. And when we see the output configuration of the typical digital circuit, we see that we can switch the lower switch on to make 0 signal, or to switch on the upper button to generate 1 signal, and that's it. But when both switches are off, then the signal is in floating state. And please note that it's not a 0 state, it's floating states. It's undefined, and in most cases, it is not allowed in digital circuits to have a floating state. Its states should be defined. The only exception is when we connect several outputs together, then all outputs should be floating except one, which should define the logic state of that line. But we are not using switches, but transistors in our circuit. So we have 2 transistors instead of these 2 circuits. And when we connect those 2 transistors, we have the common input. Here it is for the circuit. When the lower transistor is conductive, it's when the input is high, then the lower transistor is conductive, then the output is 0. And when the upper one is conductive, it's when input is low, then output is high. So you see that output always follows the inverse level of the input. And that circuit is named inverter, or not circuit. We see it here. Look at this bubble at the output. It means that the output is inverted. This bubble always means inversion, whether it is at the output or at input. And this overlined here symbol, it means that this output is inverted also. And this is the truth table for the inverter. When input is 0, output is 1. When input is 1, output is 0. Another circuit that we have to pay attention about is AND circuit. You have 2 or more inputs, and when A and B and C and D if there are more of them. If they are all ones, then our output will be 1. That's why it's called AND circuit. And the third one is OR circuit, which says when A or B or some others, if there are some, when they are 0, then output will be 0. And that's why it's called OR circuit. So at this moment, we know about 3 basic circuits. It's NOT circuit or inverter, AND circuit, and OR circuit. And if you wonder how many more do we have to learn about, there are no more. It's a whole digital electronics contains actually these 3 circuits. And that looks simple, isn't it? That yes, but only before we start to combine these 3 gates. For instance, like this. This is Intel's processor 8286, introduced in 1982, and it contains only 134,000 transistors. I said only because today's microprocessor contains several billion transistors on the chip, on the same chip size, and they all form just these. All circuits are made just this of these 3 basic circuits. They are very important, so we should pay special attention of them. The small bubble here, you can see it here and so on, means inversion. I've said that. And this you can represent AND and NOT circuit at its output as the single circuit, then it's called NAND circuit, not AND or NAND circuit. In the similar manner, you have NOR circuit here with inversed output. It's not OR anymore, it's now not OR or NOR. There is only one more circuit. I said that there are several variants of the circuits, of basic circuits. This one is a little unusual OR circuit. It's actually not the basic circuit. It can be built of other basic circuits, so it's not basic one. The only difference between OR and NOR is this situation when you have both inputs 1. At OR circuits, output is one, and at XOR circuit, the output is 0. XOR means exclusive 0, and it's shortened for just XOR. XOR circuit is also quite important in digital techniques, and we should pay good attention about it because it's frequently used. I said that it could be built from other basic circuits, like here you see it built with 4 NAND circuits. You can build it in some other ways, not only this, but I like this because it's symmetric and somehow beautiful. So let's see now how we can build some complex circuits out of simple circuits, of basic circuits. First one is the most frequently used complex circuit. It's decoder. This decoder decodes 3 address lines to 8 single lines at the output. You see, there are addresses A, B, and C here. And when you set them to some levels, say 0, 0, 0, then output 0 will be active. When they are, for instance, 1, 0, 0, then Y1 is active. When you set to 0, 1, 0, it's 2, then Y2 is active, and so on. There is one more input here. It's gate impulse input. When it's passive, then all outputs are passive. Then it actually enables the selected output, and it enables actually the whole decoder here. Here is the truth table for the decoder. You see all possible states. Here you see this XXX means any address. When enable, this one is 1, which means passive because it's overlined, then all outputs are passive, and it doesn't matter which states are on these 3 outputs. You can only also build the complex decoder. I've told about 3 to 8 lines. It could be 2 to 4 lines or 4 addresses to 16 lines and so on. But if you need the bigger decoder, you can build it out of simple decoders. You see now you have this is the main one, which is supplied by high addresses D, E, and F. And it just addresses the 8 the decoders, which are the same, but at the lower level. They are addressed by ABC addresses. So you also have one large 6 to 64 decoder made of 9 3 to 8 decoders. The enable signal, of course, has the same function. And this is the symbol for decoder, and it's also a very important one, so we will pay attention on it. Let's go on. We've said that there is 3-state output when the output is simply disconnected, like this. This is the electronic view of the same circuit. You have another more input here, which enables or disables output. When this one is passive, then output is in high impedance here, Z output. Z means Z is a symbol for impedance, so it's used for high impedance state. Then it's disconnected simply. And you can use 8 buffers here. You see these 8 buffers. They are not look like inverters, but they are not inverters because they don't have the bubble at the output. They are actually buffers which are do-nothing circuits. They really do not. They just transfer the signal from input to output. But here only when this enable input is active. So only one of these outputs of this decoder is active. So only one of these inputs will be active, and only one of these inputs, say input 4, if it is 0, 0, 1, then the input 4 will be selected, of course, when enable is activated. And we have input 4 transferred to output. When enable is passive, then output is in high impedance state, it's deselected. And this is the symbol for the selector. Now, let's see how we will switch to arithmetics a little now. This is the simple adder. It adds 2 binary digits here, A and B. It could be 0, 0, 0, 1, 1, 0, or 1, 1. And this is the sum for that. If it is 0, 1, then sum is 1. But if it's 1, 1, then it cannot fit in the, it should be 10 binary, but sum will be 0 and carry will be 1. This is the situation for that overflow condition. And that's why we must have carry. That carry is used to be transferred to the next stage of adding. If we have more stages, if we have to add more binary digits. And that's why we must have that carry input to accept that carry from the previous stage. And this carry out goes to carry input of the next stage. And we get the adder, which looks like this. This is 4-bit adder, but it can be any other number, 8-bit, 16-bit adder, 64-bit adder, or any of them. It always had the common carry in, which propagates bit by bit here, and we have the carry out. This overflow is not significant in this moment, just it's used for subtraction, not for addition. This is the adder, and you see that operand, one operand and another operand. When you apply some logic levels to those input, you've got there some here. And if it does not fit in 4 bits, it generates the carry out. And that's all. And there are also some other outputs here, which are generated by multi-bit adder. Carry out, we've seen about it. Overflow is for subtraction only. Sign is signed bit. If you know about binary numbering system, I'm sorry, we have to assume that you know about binary numbers, so we will not talk about them. All programmers are actually expert for that thing. So sign is normally in two complements notation. Sign is the state of the most significant bit. 0 is set when all outputs are 0. So when you have 0, 0, 0, 0, then this 0 is 1. In all other cases, it's 0. And parity is actually the number of ones in the whole result. You just count how many ones do you have. And if you have the even number, then parity is set. If it's odd number, then parity is reset. Now you should imagine some other circuits here. Here is the rightmost is adder, 4-bit adder. We've just talked about it. You can only put 4 AND gates. You see, all of these circuits has 4-bit inputs and 4-bit outputs, if it's 4-bit processor, of course. And you should imagine this in 4 layers. That's why these bus lines are so thick. This one and output also. They actually contain 4 single lines. See this. So you have 4 AND gates, 4 OR gates, 4 XOR gates, complement, which is inverting every bit in the 4-bit word. Negation is when you invert all bits and add 1 to the result. Oh, well, you know it from the binary system. The two's complement arithmetics is applied. Increment number and decrement number by 1. And we have 8 4-bit outputs here, and only one of them is selected. Here, selected is negation. Could be any other also. And the selector, the main selector is opcode. It has 3 bits, which actually address one of these outputs, and we have the result. This is the electronic version of the same circuit. And that circuit that can do any of these operations is called arithmetic logical unit. It's the very important circuit. It's in the heart of the microprocessor. That's why it's blue here, and we should take good care about it. Now let's talk about some other type of logic. Here we were talking only on combinational logic. It's a logic which has only one direction of data flow. You see, you have some logic input here, and you get the same logic input here in this circuit, which is very simple, of course. It's just the circuit which does nothing, because it inverts here this 0 and creates 0 again at the end. But what happens if we connect the output and input of this circuit? Think for a moment. If we have 1 here, then we will have 0 here and 1 here. So this circuit it self-supports itself. It's a stable state. But what if we have 0, then we have 1 here and 0 here, then it's again stable. So it has 2 stable states. And it's so important. It's such a big step in digital processing that it's that red circuit here, the most important in digital electronic, as it actually made computing possible. That's why it deserves this place of honor. Think about it. I'll keep for a few seconds. So it's a circuit which has 2 stable states and which enables whole computing today. We can represent it in another way. It's the same circuit actually, but drawn so that it is symmetric. We'll need it later to simplify the diagram. And these are 2 possible states of this circuit. But the disadvantage is that we don't have no inputs here. So we can have 2 outputs, and we can read actually one of two states. This is, let's consider this one as the main output. Here it's 1, and here the state of the circuit is 0, but we don't have inputs. And we will switch those inverters for NAND circuits. It's the same circuit, and it behaves the same, but now it has reset and set impulse. Here is inputs, here is reset, and here is set input. And when these inputs are high, then these circuits act as inverters and they do nothing, they just keep one state. But when you drive some of them low, look here in the diagram, when you bring set input to low level, it's overlined, so low is active, then the whole circuit is set. Q is high. And when you drive reset low, then Q is low. And so we can set or reset the whole circuit, and we will follow only Q output. This one is always opposite of it, so we don't care about it anymore. And here we are at the first demo circuit here. This is the same circuit, but just modified so that it's good for demo. I'll switch back to camera for a moment, and I'll show you how does it work. You see, here is the same circuit as you've seen on the schematic diagram, and you can reset or set the circuit. You see, now set, reset, set, reset. And when you don't touch any button, then actually it just memorizes it holds the last value when I pressed one of these buttons. Now let's go on with the schematics. It works well, but it's not what we want. We don't want the negative level to reset or set the circuits. What we need is to load data level when we want. This data should be 0 or 1, but when you press this load button, then it will be transferred to this main output, to this LED. So when the data is high, then this circuit is transparent. It actually transfers data immediately to output without any other, actually, I'm sorry. When it's high, then it transferred when it's high, it keeps the output, sorry. But when you press this load button, it's transparent. When it's low, it's transparent. This flip-flop is the same one, but without buttons. It's with the logic level here. When load input is high, then the circuit is transparent, and when it's low, then it memorizes the last value when it was transparent. That's much better. Now we can fetch data here in this circuit with load, but it's still not what we need. The problem is that it becomes transparent here at the beginning of load input here. And it flips its states at the same moment. We need something faster than this, which will do the same thing in 0 time. You see, this is the same circuit, but with the slightly optimized with 1 gate more, and that's all. And now I will demonstrate this circuit also to you. Just a moment. So here is the similar circuit. This switch here, the small switch here, is data input. It does not change. When I press this button, it changes, it's transparent. But when I don't press the load button, this is load button here. When I don't press it, it memorizes. It does not change. But at the time, at the moment of pressing, it fetches the button state. It's much better. That's what we need, really. But like I said, it's not the best possible thing, because we need it to be done in zero moment. We'll see why. You see, look at this circuit. It contains actually two flip-flops. It's called master-slave circuit because it has two flip-flops. This one is master, the lower one. So when the clock is high, then this one is transparent, and when clock is low, then this one is transparent. What we get with this is that only at the edge of clock signal. Look at this diagram here. No, look at this diagram here and here, all green points. It flips only at the falling edge of this clock signal, only at the edge. That means that it can be written and read at the same moment, the same. It's so fast that it can actually it can actually fetch its own state like this. We'll soon see that example, but sorry, it's too fast. This circuit is also very important, and we'll see that it is very frequently used in microprocessors. It's used to build the registers in microprocessors because they have to be that fast and they have to be capable of reading and writing at the same moment without any error. Here's the example here of that circuit. I will show you soon, but just let's discuss one. You see this circuit here described as denoted as the bouncer. I have the clock button here, but the problem is that when you press the clock button, this signal in this point here goes something. It does not go like this. It goes maybe like this. It has some dirty signal and then goes to low signal because the button has some bouncing when you press it, and there instead of one clean signal you have several hundred of very dirty signals. This debouncer cleans that and it corrects that error. We don't have to talk much about it because it's actually not a part of the microprocessor. It's just used for demo here, and that's all. Now I will show how this circuit looks like. This is also the data input, you see, and this is the clock input. And when I connect the not Q output, which is inversed output, to the input like this, and I will just remove this white LED which displayed the Y position. We don't need it now. Now see how it works. At every press of the button, it just copies its inverse state, so it just flips the state. And it's actually very useful circuit because we can use it to build, just a moment. We can build this is the same circuit with connected not Q output to data. We can use it to build some kind of frequency divider here. I've said every falling edge of clock signal flips the state of output. So if we connect this output to the next stage, then it will do the same thing. but with the lower frequency. And we get the binary counter, actually. This is 4-bit binary counter. The clock comes from the right side, and it switches output first, second, and so on. And the logic diagrams for these outputs look like this. With every falling edge of the clock signal, we have the new state of output. We had the output state, which is binary incremented by 1. 1, 2, 3. You see, 3 is because state out 0 and out 1 are high, and out 2 and 3 are 0, and so on. This works as a binary up counter, and that's what makes digital counting possible. I will show you how that counter looks like. Look at here. This is the 4-bit binary counter. And when I press button, each time you have the new binary number increased by 1. If you are familiar with binary arithmetics, you can see how it counts. But it can not only count, it can also, it has another input which resets the whole circuit. When I press this reset button and press clock, then it resets to 0, 0, 0, 0 always. And another input, which is load input. I have 4 inputs here. You see this dip switch here with 4 switches. When I press this load button, they are set to 1010. And when I press it, it just loads this binary input, and we can load it to any desired value. Now, let's go back. And see what else can we do with parallel, with that master-slave flip-flops. We can use we can use several of them to build a parallel register, to fetch the whole word, several bits at a time. And it's very frequently used in microprocessors, as it's a kind of parallel register. There are a lot of registers in every microprocessor, and actually the whole data memory is a series of parallel registers. Now we are starting to build our processors, and we have to do it fast. We'll see. A register is accumulator, which is the most important register in the computer. And here is arithmetic logical unit. And it can, at every clock cycle, it can at the same time read accumulator. And for instance, if opcode is adjusted for adding, it can add it with operand B. And the result will be written here. Then the next instruction could be incrementing the AND or something like that. So it crunches number at series with every clock cycle. But one register is not enough. We added B register here also. We will need more registers. I said there are a lot of registers in microprocessors. Some of them contain 32 accumulators only. And a lot of other registers. We said that arithmetic logical unit creates some flags, and they are also fetched in the special register, which is also parallel registers. And we will move it aside to make room for some other circuits. This is data memory, which can be read to read and write data, and program memory, which can only read. From memory, microprocessor is not allowed to write something to program memory, at least in most cases. You have some special way to write something to program memory at most modern microcontrollers. And there is a bus line here, which is internal data bus, which connects all registers and also goes out. Here are some supposed pins to address external memory. And we must have the clock signal, which is the main conductor of the system. We must go really fast now. This clock signal feeds the 2-bit counter, which counts to 4, and the decoder decodes those 4 steps. Those steps are actually the main sequence of the microprocessor. At the first step, the clock signal, it reads the program memory here. At the data out, it reads it somewhere, and we will skip the next the cycle here, the next phase. This output, the next output is execute sequence. It just reads from memory if one of operands is from memory, or it reads from the accumulator and so on. And the last output just triggers write result to memory or to accumulator or somewhere in some of these registers. We have also parallel register, which fetches the contents from the program memory, because program memory had, when it's read, then these outputs should be stable enough, as program memory is slow memory and it has to prepare the next program word for the processor. I'm told that the instruction decoder is the second step. This is one of possible variants how instruction decoder should be connected. There are many decoders actually in instruction decoder of the microprocessor. The one part of the program word here, one part of the word, it's only 3 bits of 8 bits here in total. It defines which instruction is in progress, which the instructions should be performed. See, if it's 0, 0, 0, then it's arithmetic logical instruction. And in that case, it counts what opcode is here. Is it addition, ending, ORing, and so on? Here you see it's here. Here you see the choice of ALU operations and so on. And if it's some other instruction, then then these 3 bits are fed to some other part of the computer, some executive part. The addresses are also mostly, this is hypothetical 8-bit processor actually, and these addresses are 16-bit. It's not enough to have 8-bit addresses. And here in program memory, there are also 16-bit addresses. So we can address it directly from the program memory when we say, write this data to say address 0007. And then it's direct addressing. But there is also indirect addresses when the instruction says, write this data to memory addressed by accumulator and B register, for instance, or so on. It's indirect addressing. That's why we have selector here, because one of these bits addressing mode here can be direct or indirect. And just a moment. Yeah, good. And there are some from the instruction decoders, there are some other signals which just set some other parts of the microprocessor, which enables some part of the microprocessor depending on the instruction in the program word. We'll not waste much time about it because we don't have much time. There is program counter here. It's a very important part also. Just let me find my, here is my cursor, is very small so I can see it. A 16-bit program counter which defines which program word will be read from the program memory. For the beginning, this reset signal just resets the program counter to 0000 so that it starts operation from program word 0. And it can be also loaded by some other value and so on, or incremented. I said that in direct mode, the program has to define the address in direct mode. It's here and here. Has to define 16-bit address, but by 8 bits. It cannot be obtained without loading registers in several steps. So it reads not only 1 byte, command byte from the program memory, but also 2 more bytes which define the address for data memory or for program memory. And at last, there is 1-bit selector here, which selects the carry flag, which should be output here to load the program counter if the instruction is jump. Jump instruction is just has not only to increment the program counter every time after the instruction, but to load it with some new value, which is also defined by parallel registers here.
2-minute warning, Voja.
Okay, I'll be finished soon. And these 2 registers are used to define the 16-bit program counter address for 16-bit jump. Now it's the whole story about the microprocessor. This is just the structure of, if you see the structure of the machine program, you will see that it contains only arithmetic logic instruction, data copy instruction, and conditional branch instructions. And that's all. Unconditional jump is just a special case for a conditional branch. Combining those 3 types of these types of instructions, you can create any possible logic flow. You see, just like we created the microprocessor by using only 3 basic logic gates, we can use these 3 types of instructions to build some higher level program and so on. And all we learned about the microprocessor is actually here, this little house. And what we have on the market now is a very complex house, but it's still a house. It's still a house that works on the same principles as this one. And that's it. I just wanted to show you. My idea was to talk a little bit about the badge for which was made for the last year's conference, but unfortunately, you know why it was canceled, because of the virus. And I want to tell you that that hypothetical processor, which is simulated by 16-bit processor here, which can be programmed, which can be single-stepped, which can be slowed down so that you can see how the arithmetic logic unit works, how accumulator works, flags, program counter, and the part of data memory here on this display. I hope that we will soon have the not online conference, but the real conference, just like we had before, and that this badge will be active there. Thank you very much for this and for your attention. Bye.